Welcome to qnawire.
Going to be looking at refraction and in particular Snell's law with a fairly complicated set of boundaries, not too bad. But what is happening is there is one of these underwater lights inside of a bucket, and the light is propagating up through both the water and the layer of ice before it gets into the air. Now, at some point, the angle of the rays will not be able to make it out because of total internal reflection. So let's take a look at Snell's law. It says that between two sides of an interface, the index on one side times the sine of the angle with respect to the normal is the same product of index and sine of angle on the other side. Now, what can happen if one of the indices is smaller than the other? So if you are starting in a denser material, going to a less dense, what will happen is there will be a critical angle. So let's say N1 is denser and N2 is less dense. What will happen is the angle can come out at a 90 degree. So N1 sine of theta 1 is equal to N2 times sine of 90 degrees. And this can happen because the angle on the right-hand side can be less than the angle on the left-hand side can be smaller than the angle on the right-hand side because of the denser material. And this is called total internal reflection. That angle inside the denser material at which this happens is called the critical angle. So let's take a look at the ice-air interface. Ice has an index of refraction much higher than air, and so the ray can get trapped inside of the ice, such that N1, well, let's just go ahead and put in for the N of ice, 1.309 times the sine of the critical angle is equal to the N for air, which 23 sig figs after the decimal place, 1.000 times, of course, sine of 90 is 1. And then we can see how this critical angle can occur. Sine of angle must be less than 1. And this works out to be an angle of, let's try 4 sig figs just to be sure. 49.81, we'll call it. So pointing out in my figure, the theta critical for the ray of light inside the ice is 49.81 degrees, in which case it comes out into the air at a 90 degree angle. Okay, let's now compute the angle that the ray must be coming into the water. And for that, we're just going to use simple Snell's law. But we can see if the ice is a nice flat piece of ice, we'll assume that, then the ray coming from the water goes into the ice at the critical angle. So that makes life a little bit easier. So water into ice. N1 is the N of water, 1.333. And we are looking for the theta 1. So that's our question mark. And that has got to equal 1.309 times the sine of 49.81 degrees. And we can solve that for theta 1. Let's be sure to do that with the correct number of sig figs. And we get 48.60 degrees. Whoops. Theta 1 equals 48.6 degrees. Okay, and then we can also ask, what if the ice melts? Would we be able to see anything different? Well, it turns out that without that ice layer there, your critical angle will then become the 48.6 degrees. That is the water-air interface will create that critical angle. And we can go ahead and show that. What if the ice melts? So there's only the water-air interface. So again, air is the less dense material. We have 1.333 times sine of theta critical, new theta critical, is equal to 1.000. And solving for that critical angle, no surprise, it is 48.60 degrees. So probably not the best way to test whether the ice is there or not. With this optics experiment, you'll have to think of a different experiment.